All right, let's dive right into a really cool foundational concept in computer science, the AVL tree. Now, this thing was invented way back in 1962, and it was the very first self-balancing binary search tree. And you know what? It's still super relevant today for solving a very specific kind of problem.
So let me ask you this. What if your search tree could literally fix itself? The second it starts to get a little bit lopsided. What if it had this built-in reflex to just snap back into perfect shape? Well, that's exactly the promise of an AVL tree.
And why does this even matter? Well, you can see the difference right here. It's like night and day. On one side, you've got a beautiful, balanced tree. Searching through that thing is ridiculously fast. We're talking O log n time. What that really means is you can double the amount of data, and it pretty much just takes one extra step to find something. But then you look at the other tree, and wow, that is a total disaster. It's basically just a glorified linked list. Searching is painfully slow. ON time. You double the items, you double the search time. That's the exact nightmare scenario AVL trees were designed to prevent.
Okay, so here's a simple way to think about this for the rest of our chat. Just picture an AVL tree as a special kind of bookshelf. And this bookshelf has one and only one core mission. It must never lean too far. Because let's be real, a leaning bookshelf isn't just an eyesore, it's totally impractical. Try finding a specific book on that thing. It's a mess.
All right, so that brings us to the tipping point. How does our tree, how does it even know when it's starting to lean too far? There has to be some kind of measurement, right?
And there is. It's this super important metric called the balance factor. It's actually really simple. For every, and I mean every, single node in the tree, you just look at its left side, measure its height, then look at the right side, measure its height, and subtract one from the other. That one little number tells you everything you need to know about how balanced that part of the tree is.
Okay, so this whole elegant system really boils down to one simple rule. It's all about what that balance factor number is allowed to be. So what are the legal values for this balance factor? Well, if you get a +1, that just means the left side is one level taller than the right. No big deal, perfectly fine. Our bookshelf is stable. Now, if the balance factor is a perfect 0, that's the dream. Perfect symmetry, left and right sides have the exact same height. That's our perfectly upright bookshelf.
And hey, if it's -1, meaning the right side is one level taller, that's also totally fine. It's a tiny lean, but nothing to worry about. The tree is still considered balanced and super efficient. But what happens if that balance factor hits +2 or -2? Ah, that's the alarm bell. That's the red flag. The tree has officially broken the rule. Our bookshelf is leaning way too far, and it's time to trigger an immediate fix.
So the alarm goes off. The tree is unbalanced. How does it fix itself? Well, this brings us to the coolest, most elegant part of the whole system, the art of rotation.
Rotations are basically the tree's magic trick for fixing itself. They're these tiny, localized adjustments. Just a few pointers get shuffled around right at the spot where the imbalance happened. They're incredibly fast, what we call constant time operations. But here's the absolute genius part. They do all this while perfectly preserving the binary search tree property. That means after the fix, all the smaller values are still on the left, and all the bigger values are still on the right. The fundamental order of your data is never, ever messed up. And it turns out there are only 4 ways a tree can get out of balance. We give them these simple names: left, left, right, right, left, right, and right, left. And really, the name just describes the path you take from the unbalanced node that caused the problem. And for each of these 4 cases, the tree has a specific playbook, a specific move to fix it.
Now, the first 2 cases, left, left, and right, right, are what you might call the outside cases. And thankfully, they're the easy ones. All you need is one single rotation to fix them. It's literally like giving our leaning bookshelf one simple, firm nudge to get it standing straight again. Super simple, super effective. But the other 2, the inside cases, left, right, and right, left, they're a little trickier. They have this weird kink in their shape, so a single nudge won't work. For these, we need a double rotation. Think of it like a 2-step move for our bookshelf. First, you do a small tilt on a lower shelf to straighten out that kink, and then you do the big counter tilt on the main shelf to get the whole thing aligned. And just like that, everything's perfectly straight again. Okay, so all this work, this constant checking of balance factors, these clever rotations, it's all for one reason: performance. So let's talk about the practical payoff. What do we actually get from being this obsessed with balance? And here it is. This is the payoff. Because the tree is always kept so strictly balanced, every single important operation, searching for something, inserting something new, deleting something, is guaranteed to be fast. We're talking O of log n. There is no dreaded worst-case scenario where it suddenly slows down to a crawl. That guarantee is literally the entire reason AVL trees were invented.
And just how strict is that guarantee? Well, it is mathematically proven. The height of an AVL tree is guaranteed to be less than or equal to about 1.44 times the log of n. The math behind this is actually super fascinating. It involves Fibonacci numbers and the golden ratio, but what it boils down to is this. The tree will never be more than about 44% taller than a theoretically perfect tree. That is an incredibly tight, predictable limit, and it's why you can always rely on its performance.
So, does this mean you should use an AVL tree for absolutely everything? Well, not so fast. This brings us to a classic engineering trade-off. Let's compare the AVL tree to its famous cousin, the red-black tree. The choice is pretty clear. AVL trees are more strictly balanced, which means they are faster for lookups, period. But red-black trees are a bit more chill. Their rules are looser. This often means they do fewer rotations when you insert or delete stuff, which can make those operations faster. It really all comes down to what you're doing more of, reading or writing. So, when should you pull an AVL tree out of your toolbox? Well, if your application is doing way more reading than it is writing, we call these lookup-heavy workloads, then the AVL tree is an absolutely fantastic choice. And anytime you have a situation where a strict worst-case performance guarantee is critical, where you simply can't afford to slow down, think things like network routing tables or the indexes in an in-memory database, that's where the AVL tree really shines.
All right, let's wrap this up. If you remember just 3 things, make it these. First, it's all about that balance factor. It absolutely has to stay at -1, 0, or +1. Second, if that rule gets broken, rotations are the super fast constant time fix that puts things right without messing up your data. And third, those 2 things together give you that ironclad guarantee of O of log n performance for all your operations.
And that leaves us with one last big question to think about. We've seen that this whole strict balancing act gives us an amazing guarantee of speed and predictability. But all that balancing is constant work. It's overhead. So the question you have to ask yourself as an engineer is this. For my specific problem, is that guarantee of near perfect balance always worth the extra work?